You asked for videos on ACLs and NAT on ASA firewalls? Well, I've heard you and here it is. In this video, we start with ACLs and we move to NATs in part 2. But let's not waste any time, let's get right into it. We're going to approach ACLs by using a lab. We have an internal network, which is a switch and 2 workstations. This is safely placed behind our ASA firewall on the inside interface. We also have a server. This is our intranet web page and is also our DNS server. It needs to be accessible by people both inside and outside the network, so it's located in the DMZ. Or perhaps DMZ if you prefer, but I'm Australian, so I'm going to say DMZ. On the outside interface, we have a router to represent our connection to the internet, and a web server to represent a resource on the internet that we want to access. We're keeping this simple so we can focus on the ACLs. So, some of this lab is pre-configured. We're decrementing TTL by default, and ICMP inspection is enabled. We're also only going to use IPv4. I have made this lab available for Patreon supporters to download. If you haven't heard of Patreon, it's a service where you can get involved and support network direction. It helps me to buy better microphones for recording and things like that. So to thank you for your support, I have some extra content, including this pre-made lab that you can download and use yourself. And if you're not ready to do that, if you don't want to support the channel yet, that's fine. These videos are still free and you can build your own labs based on them. And if you have any questions on this, just let me know in the comments. So you've told me that you want to see how ACLs and NAT work from the command line. And that's fine, but I'd like to quickly say, don't be afraid of using the Asdm. I know it's an old Java app, and it doesn't always go as smoothly as we'd like, but it generally works. Personally, I use a mixture of CLI or Asdm, just depends on what I'm trying to achieve. Some things are simply easier with the Asdm, and I'll point these out as I go through. So in this lab, there are 7 things that we want to accomplish. We want to allow everything to be able to ping everything else. We want to allow our workstations and server to run traceroutes, but we don't want anything on the internet to be able to traceroute into our network. Everything should be able to perform DNS lookups to the server in the DMZ. Workstations should be able to retrieve a web page from the DMZ server and the web server on the internet. Finally, the website on the intranet server should be available to resources on the internet. Now, before we get into configuration, I just want to very quickly give a shout out to Atayu, Simon, Brandon, Srinath, Michael, and Prabha, who have recently become Patreon supporters. I'm really sorry if I've pronounced any of your names incorrectly, but I really appreciate your support. You help make videos like this possible. Okay, so right now, there are no ACLs configured. What we do have configured is the interface security levels. The inside has a level of 100, the DMZ is 50, and the outside is 0. When there's no ACLs applied, traffic from a higher interface level will be allowed to pass to an interface with a lower security level. However, the reverse is not true. Traffic from a lower security level cannot pass to a higher security level. We can see this when we use a workstation to ping a server on the internet. In this case, ping succeeds. But if we try it from a server on the internet, we can see that ping fails. Traffic is trying to go from a lower security interface to a higher one, and that's just not permitted. So this is a good default place to be in when you first turn on your router, but for most cases, it's too simple to really work. And that's why we use ACLs. They're far more granular. So we need some ACLs to achieve our goals. But which type? After all, there are a few. The standard ACL, for example, is used to identify traffic, usually to determine which traffic goes over a VPN, or matching traffic in a route map. So it's not really used to permit or deny traffic, as much as it matches or not matches traffic. The extended ACL is the one we want for most traffic filtering. It can match on source or destination IPs, ports, FQDNs, time, and others. This is the type we'll be using throughout this video. The EtherType ACL matches non-IP traffic on bridge groups, and the WebType ACL filters traffic on a clientless SSL VPN. And of course, I need to quickly mention management ACLs. They're not a special ACL type, but a special way an ACL is used. A management ACL is used to filter management traffic going to the ASA itself. So if you want to restrict the IPs that can access the ASA with SSH, for example, a management ACL is one way you could achieve that. Now, I need to quickly clear up the difference between an ACL and an ACE. We often misuse the terms. I'm quite guilty of this myself, so I want to be clear on the difference between the two. Here we see 3 rules. They're not in ASA syntax, so you can't just type these into a CLI, but they should paint a good picture. Each line is an access control entry, or ACE, often called an ACE. Each ACE is a rule that permits or denies traffic. A group of ACEs form an access control list, or ACL. I've heard some people calling this an ACL. We'll see soon that the ASA gives each ACE a name, and all the ACEs with the same name are part of the same ACL. The entries are in a list that are evaluated in order from top to bottom. An action is taken based on the rule that matches first. So you need to structure the rules in a way that achieves what you want. In Rule 3, devices in 10.60.00/16 can reach a web server on HTTP and HTTPS. However, we have a /20 subnet that should only access the web server on HTTPS, not HTTP. So Rule 2, being evaluated first, will deny HTTP traffic from this subnet. But to make it more complicated, there's a /24 subnet within that network which must be allowed to access the web server with HTTP. So it needs to be evaluated before the other 2 rules. Do you see how changing the order of these rules will change the outcome? You need to think about this when you're creating your ACL, and often you'll want to put the more specific entries higher up the list. Well, let's get into some config. We'll start by creating a simple ACL that allows everything to ping everything else. I'll walk you through the details of doing this. We're creating an ACE called Global Access. This is our first rule, so this creates the Global Access ACL. We can add more entries to the ACL at any time later just by creating an entry that uses the same name. When you're creating a new ACL, make sure to choose a good name. It should make sense for when you're troubleshooting later. I'm adding the extended keyword to tell the ASA that this will be part of an extended ACL. On a modern ASA, we don't specifically need to include this as the ASA will usually work out what we wanted anyway. Next, we need to give an action, which can be either permit or deny. The meaning here should be quite obvious. Now we need to start telling the ASA what type of traffic we're talking about. There are several different options here, but the common ones are ICMP, TCP, and UDP. Ping uses ICMP, so that's what we're going to select. Next, we have the source and destination, and it always goes in that order: source, then destination. We want to allow ping to work everywhere, so we'll say from any address to any address. And that's the rule done. We can see the entries in the ACL with show access list, and then the ACL name. We can see that there is only one entry created so far, which is the rule we just made. We'll see more entries in here as we create more rules. But creating an ACL is not enough on its own. Before it does anything, we need to apply it using the access group command. We give it the name of the ACL, then we decide where to apply it. Usually, we would apply it to an interface with a direction. This way, the rules will be evaluated as traffic enters or leaves a particular interface. But this time, we want the ACL to be applied everywhere, regardless of which interface the traffic is on. So we apply this to global. We can see which ACLs are applied and where they're applied to with show run access group. Here we see our ACL applied to global. There can only be one ACL applied to global at a time, so if we configured another one with the access group command, it would overwrite this setting here. When traffic passes through the ASA, ACLs applied to interfaces are evaluated first. If none of those rules match the traffic, then the ASA will evaluate the rules in global. If there's still no match, the traffic is dropped. You do need to be careful when you're applying rules to global. We don't want to overuse it, as we should try to be specific with the traffic we allow through. After all, this is a security appliance, and we don't want to undermine that by creating too many rules that allow traffic everywhere. Right, let's test our rule by connecting to the web server again. Now ping is working. Not everyone likes to allow ping everywhere like this, so whether you do this is up to you. If you don't like ping, you should still not block ICMP entirely, as it breaks network features like PMTUD. I'm not going to go into the details of that right now, so let me know if you want a separate video on that. Applying ACLs has an interesting side effect. Now the security levels generally don't matter anymore. Take a look at workstation 1. If we do a traceroute here, it fails. And why is that? Because the security levels are no longer as important as they were. So for traceroute, we now would need to create a specific rule to allow it. However, there is a small catch with this. Security levels aren't important unless you're trying to get traffic to pass between two interfaces which have the same security level configured. By default, this will be denied, even if an ACL is applied. I won't get into any more detail on this here, but once again, let me know if you want to see how that works in a separate video. Okay, let's create an entry to allow traceroute from anywhere on the inside interface to anywhere else. Windows and Linux use different methods for traceroute. Windows uses ICMP, which we have already allowed, so traceroute will already work for Windows machines. But we're using Linux here, and they use a range of UDP ports as well as ICMP messages. If you want a video on how traceroute works, well, you know what to do. The process is the same as it was before. We'll create a new entry in a new ACL called traceroute. We're permitting UDP from any source to any destination. Later on, we'll apply this to the inside interface, so this really means any source traffic that arrives on the inside interface. But we're not just going to allow all UDP traffic. We want to restrict this to a particular range of ports, which we can do with the range keyword. Traceroute ports are from 33434 to 33464. And as before, we need to apply this list to an interface. This time though, we want it to apply to traffic coming in on the ASA on the inside interface. Understanding the difference between the in and out direction can be tricky at first. Imagine that you are the firewall and someone hands you a packet. That packet is coming in on a particular interface. Now, let's say you want to hand that packet to someone else. That packet is going out a different interface. So on the ASA, we can apply these rules in either of these directions, or both of these directions. So, for example, we can have an ACL for traffic coming into the ASA on the inside interface, and a completely different ACL for traffic going out of the ASA on the DMZ interface. Does that make sense? Over on the intranet server in the DMZ, we can see traceroute working here as well. But what about from the web server in the internet? That will still fail to pass through the firewall, as there's no ACL to allow it. But that's fine, because that's what we wanted. Unfortunately though, this leaves us with a small problem. I did not choose a good name for the ACL that I applied to the inside interface. I called it Traceroute, which describes what that one entry does, but it doesn't describe the entire ACL. So, we should rename it to something with a better name. And that's really easy. To do that, we just use the rename keyword and we give it a new name. Show access list is looking a bit more complicated now, but if you look closely, you can see our new ACL name right here. Let's tackle some web browsing. Over on Workstation 1, we can test web browsing with the Linux command curl. This just tries to retrieve a web file from the command line, and as we would expect, it fails. So of course, we need to create an ACL or an entry for web traffic. Web traffic can be HTTP or HTTPS, and we should allow both of these from the inside network. We could do this by creating two different rules, one for HTTP and one for HTTPS, but there is a simpler way. We start by creating an object group, which is a reusable block of information that we can use across many different rules. They're great if you want to make a small change to, say, an address or a port number. In that case, you just change the object or the object group rather than going to every single rule that uses it and changing them all. In our case, we're creating a service group. A service group contains services, which is what the ASA calls ports. So we're going to call our service group web, and we're going to say it contains a list of TCP ports. Within the object group, we should add a description, and then use the port object command to add both HTTP and HTTPS. The ASA has some predefined names and port mappings. So when we type in HTTP, it automatically understands that we mean port 80. And HTTPS means port 443. So it's handy there. It saves you a bit of time. You could use the actual numbers though if you wanted. It's completely up to what you're comfortable with. Right, so let's create the firewall rule. First, we'll add a special entry called a remark. This is a comment that explains what the following entry will be used for. This is extremely useful for troubleshooting later on, so I recommend that you add one of these every time. Now we add the permit rule. This is for TCP traffic from anywhere to anywhere, using the object group that we just created. We've only had to create one single rule, but we've allowed two different ports using that group. If we test CURL on the workstation again, we can see that it can successfully retrieve the web page. How about we take it one step further and allow devices on the internet to browse to our intranet server? I'm testing this with CURL again, but I'm using the K switch, which just means ignore any certificate errors. We need certificates because we're talking with HTTPS traffic. Okay, so I've found sometimes with Viral that the first letter of a command does not get typed in properly. That's just something you have to keep in mind if you're doing this lab. I'm probably going to do this a lot through the next few videos, so please bear with me. Alright, and you can see that it fails, which is what we expect. Now we're going to make it work. Before we create the rules, let's create a network object for the intranet server. Just like before, this is a reusable object that can make the configuration easier. In fact, we're going to see it a bit in the next video too, when we use it to configure NAT. Using the host keyword in the rule means that we're supplying a single IP address, not a range or a subnet. Now we can create the rule, starting with a remark. You can use several remark lines and use leading spaces to keep things tidy if you want. It's just up to whatever you want to do. And here we go with the rest of the rule. We're not using from anywhere to anywhere this time. From anywhere, yes, but the destination is the object that we have just created. So we're setting the destination as our intranet server. And this time we're only allowing HTTPS. That's because it's good practice to disallow regular HTTP into your network from the internet. And the reason for that is because regular HTTP is not encrypted. The only exception I can really think of that I would use to that rule is if your web server has a rule that enables it to redirect HTTP requests to HTTPS, which is a great thing because if anyone tries to connect on HTTP, they'll end up getting redirected to HTTPS anyway, which is very secure, and that's a good practice. And of course, this is our first rule that we're going to apply to the outside interface. So, well, we need to do that exactly. We need to apply this to the outside interface. And now if we have a look at our ACLs, we can see a few new entries. Do you see how each entry has a line number? This controls the order in which the entries are evaluated. New entries are added to the end of the list by default. If you want to move a rule within the list, well, the simplest method is to use the Asdm. It has a simple up-down button. Just simply slide those rules up and down. But if you're really committed to using the CLI, you would need to remove the ACL and re-add it to the right spot by giving the entry a line number. Try it out in the lab and see how you go. Do you also see how each rule has a hit counter? This is useful during troubleshooting. to see how many times this rule has been matched. So let's quickly double check that we can access the intranet server now from the internet. It looks like the web server is rejecting our request. Hold on for a moment. I'm going to pause the video and find out what's wrong. Okay, I've got it. I forgot to enable HTTPS on the web server, so it wasn't a firewall issue, and it's looking good now. Right now, we can connect to the intranet server using an IP address. But we cannot connect using a host name. We can see this by pinging the host name from a workstation. The reason for this is DNS. The intranet server is our DNS server, and our workstations are configured to use it, but the firewall is blocking DNS requests to the workstation. And that's what we're going to fix now. DNS requests should be allowed everywhere, at least in our case, so we're going to make this a global rule. DNS mainly uses UDP on port 53, so we're allowing that to our server object. We should also add a second rule. Hang on, something's not quite right. Yep, okay. I spelled the name ACL incorrectly. Okay, I'll add it in again with the right name. And now for that second rule. Some DNS requests will use TCP port 53 instead of UDP. This is to support occasions when the responses are very large. And this doesn't happen all the time, but it's still best practice to add this rule. If you'd like to challenge yourself, try to find a way to use one of those service group objects to add in a single rule instead of the two rules like we've just done. See how you go. Put your solution in the comments if you come up with something good. Now, have you noticed that we're not making rules to allow return traffic? This is because the ASA tracks a connection once it's built and automatically allows the return traffic through. It assumes that if we trust the first packet in the connection, the rest of the packets should also be trusted. Anyway, on the workstation, we can see that we can now resolve the host name to an IP address, so our rule is clearly working. We're allowing our inside workstations to access the intranet server in the DMZ, but we're doing this by IP address. What if our web page was on several servers with different IPs, like a web farm? Or what if the IP address changed regularly for some reason? Maybe it's in the public cloud where there's DHCP enabled. One option is that we can allow or deny web traffic based on the URL that clients are trying to reach, rather than by IP address. So first, let's remove the web browsing rule that we already have. We'll replace it with something different. But before creating a new rule, we need to enable the ASA to do DNS lookups. Start by using DNS Domain-lookup DMZ to tell the ASA to perform lookups using the DMZ interface. Next, we edit the default DNS server group. We add our name server, and then we add the DNS suffix. Step number 2 is to edit the intranet server's object, and we're going to give it a bit more information. We're telling the ASA that this server's name is intranet.networkdirection.net. Now to put the firewall rule back in, only this time we're not allowing access to the IP address, but to the host name. We should probably check that the ASA can resolve this name. Try pinging it from the ASA. That's good, so now try the show DNS command. This confirms that the ASA can resolve this name to an address. Over on the workstation, we get final confirmation that this is indeed working. Another cool thing that we can do is to allow or deny traffic based on the time. We might want to restrict access to social media during lunchtimes only, for example. It's really hard to show this in a lab, so I'm just going to talk about it for a moment. The thing I like most about time-based rules is something I like to call a time bomb. Often people come to me and say, I need access to this particular server. And when I ask what ports and IPs are we talking about, they usually say, I don't know right now, I don't have time to figure it out. You may have been in a scenario like this. I could just deny their request and say, no, that's insecure. But in a business, money is involved. And if the important people can't do what they need to do, they get upset very quickly. And they're the ones who pay us. So we've got to be nice to them. So the compromise I use sometimes is to set a time limit. I say, sure, I'll set up that rule. That'll get you going. But you've got to give me more information so I can make this more secure. When I configure the rule, I put an expiry date on it. So it'll stop working in a few days. That means they've got a few days to get the information that I need before their access breaks. And that's usually enough motivation to get them moving. One last thing I want to show you is Packet Tracer. This is used to simulate traffic through the ASA and to tell us if it will work or not. This is far easier through the Asdm, in my opinion, but the CLI is fine too. So I'm going to simulate traffic from workstation 1 to the internet, so we can see if the ASA thinks that traffic will be allowed. We always start with Packet Tracer input, and then give it the interface we expect packets to arrive on. Next, we give it a protocol like TCP, and the source IP and port. Source ports are usually random, so often you can use whatever value you want here. And then we finish up with the destination address and port. The output we get here shows us several phases. These are the steps that the firewall goes through when handling a packet, such as evaluating an access list or doing a route lookup. For each phase, Packet Tracer will tell you if it thinks that the packet will be allowed or dropped. If a phase does result in a drop, it will give you a reason. In this case, it's saying the traffic is dropped by the implicit rule. That means that there's no access control entry to allow this traffic. Remember that we removed it before we added the FQDN rule? Finally, there's a summary at the end with the action and the reason. So let's try it again with some different conditions. This time we'll test access to the intranet server. You'll see that there's a lot more phases now, and that's because this traffic is allowed through the ASA. Get used to using this tool, because it's fantastic during troubleshooting. And what you've seen is the general idea of how the ASA handles ACLs. For a bonus, let's enter the command clear configure access list. This one is very dangerous, so I'm really just showing this for fun. It erases all the access lists from the ASA and it doesn't warn you about it. You can give it an ACL name if you want to erase just one ACL. Well, I hope you liked the video. Give it a thumbs up if you did and share it with someone else who can get some benefit from it. And I hope to see you in the next video, which is configuring NAT on the ASA. Hope to see you there.